Bismillahirrahmanirrahim. So let's continue our discussion about the operation of MOSFET with energy band diagrams. So this is the picture of a MOSFET. We have a VGS applied at the gate, and this VGS is greater than the threshold voltage, and we have a VD applied at the drain terminal, which is greater than equal to 0. The source terminal is held at 0. Okay, now this gate voltage would generate an electric field that is vertical to the dimension, and we can draw an energy band diagram for this y direction. Now, if you remember, in one of the previous example, there was a similar thing that we discussed. Here was our gate, then we have silicon dioxide layer, and then there was this p-type material. So this was one of the examples that we discussed in the earlier part of this week lecture, and here it is shown again. So you see, when you apply a gate voltage, so in the absence of gate voltage, the energy bands are straight like this, but with the application of the gate voltage, the potential energy, the voltage is developed. So that voltage is Vy, and it was something like this. It was higher near the surface of silicon dioxide, and it goes down to 0 as you move away in the P material to the other side. Okay, and we saw that the potential Ey, it is denoted by here by psi of s, is it was inversely proportional to V of y. So you see, at this point, if this goes down, this band goes down, this base goes down. Okay, so the conduction, the intrinsic and the valence band goes down due to the developed potential that is developed at the gate with application of voltage. So this is the energy band diagram, normal to the channel, perpendicular to the channel. Now what happens if we want to have a look at the energy band diagram in the horizontal direction? So in this direction, that is parallel to the channel. Okay, and this is the one that will determine when the channel will support the transport of current. So again, we can draw the energy band diagram of n-type material. So our source is n-type, our drain is n-type. Okay, and this is our channel, which is inside a p-type material. So we already know that the Fermi level or the Fermi band of the n-type is near to the conduction band, and the Fermi level of p-type is near to the valence band. Same on the drain side, it is an n-type material, so the Fermi level is near the conduction band. So this is the energy band diagram of all the three regions, but separately. What happens if we join them together? Okay, So what will happen when we join them together? So these are the three separate regions, again shown in this slide, and in equilibrium the Fermi level is constant, so it stays where it is. In the n-type material it will stay where it is, in the p-type material it will stay where it is. Okay, so this is the situation in equilibrium, and this is the formula for how the conduction band changes. So this is the one when there is no psi x developed, and when there is a psi x developed, it is subtracted, and we have seen that it drops. Okay, so this is just the formula to show the graphical behavior that we saw earlier. Okay, so when we join the three pieces together, what will happen that there will be electrons from the source region, and this here is drain, it also has electron, and here in the channel we have excess of holes, so a random flow of electron from one direction to the other direction will start, and the net current will be 0. So this is called the equilibrium state. And what will happen because of this random transfer of electrons and holes from different regions, that the Fermi level will align. So the Fermi level denotes the flow of this random current, and it will align in all the three regions. In order to align, what has happened is that the energy of electrons in the drain and in the source, it has dropped. Okay, it has dropped, and it aligned itself with the Fermi level of channel. So in order to align all the three Fermi levels, the energy levels of or the Fermi levels of source and drain have dropped, and that's why the conduction and the valence band of channel has moved up. Okay, so this is another picture that shows the same. You see, this top is because the conduction band of the channel has moved up. Okay, and this is because the valence band of channel has moved up. Okay, so you see there is this kind of, you can say, potential hill that is developed. This is what the barrier is. So it is like a hindrance to the flow of electrons across the channel. This is the barrier that stops the flow of electrons across the channel. So what happens now if we increase the gate voltage? What will happen? If we increase the gate voltage, this electrostatic potential in the channel will change, and it will lower the energy of electrons in the channel. And what will happen is something like this, that when you apply a voltage, okay, the barrier will go down. Okay, so you see, this is the channel. This is the picture that shows the barrier. So on this side you have the source, on this side you have the drain, and you have a potential hill that is here. So when you apply a low gate voltage, the potential hill is very high. Okay, note that the source and drain are at zero potential. But what happens when you apply a voltage Vg, a high gate voltage? So you see, for a high gate voltage, this goes down, the potential hill goes down. Why? Because we saw that when a potential is applied, the electrons go into a potential well and they lose energy. So that's why the barrier has dropped. Okay. Now when the barrier has dropped, it makes it easy for electrons to flow from one side to the other side. But again, because there is no potential difference between on this side we have the drain and on this side we have the source. As there is no potential difference between the source and drain, VDS is 0, so ID is 0. So although some random electrons can go from here to here and some random electrons go from here to here, the net flow of electrons in both directions is 0. Okay, so because VDS is 0, there is no potential difference, the current is 0. So a high gate voltage, what is the effect of a high gate voltage? It just lowers the potential hill for electrons. Okay. Now what happens if we add a small VDS, a small voltage to the drain that is higher than the 0? Now in this case, there is a potential difference that is developed across the VDS. So our D is at a higher potential than the source. Now, and VGS is also greater than 0, so the potential barrier is low. But what happens because of a high VDS, that you see the Fermi level, so this was the Fermi level before, the Fermi level was before somewhere here. Okay, it was aligned with the source, but now the Fermi level has went down. Why it has went down? Because whenever you apply a positive potential voltage, the energy of electrons will be reduced, because the positive potential pulls it into a potential will, it lowers the energy of electrons. Okay, so that's why the Fermi level has gone down. In fact, this Fermi level is sometimes called quasi Fermi level. Okay, it's just a name. You can call it Fermi level, but some of the reference material will call it quasi Fermi level. So this is what happens. You see now that the potential hill is not like this, okay, but because of the application of drain voltage, a VDS, it is something like this in the blue one. At one edge of the barrier that is near to the drain, it is lowered. It is lowered compared to the source side. Okay. So again, if you apply a very high gate voltage and a very high drain voltage, the shape of the barrier changes further. You see that it has, the peak has shifted. The peak has shifted towards source. This is the situation in on state. So as you increase the VDS, the Fermi level will go down, and you see that it will make it very easy for electrons to go from the source side to the drain side, because you see there is a very steep potential difference, or a potential hill that has a very steep slope. Now, what happens if you have a reverse situation, which you have a very low gate voltage but a very high drain current? So the quasi-Fermi level goes down, but the potential hill is up here. Okay, and that means that for this electron to jump from here to here is very difficult. Okay, so this is the off state. Now, some of the electrons may still have a very high energy, and they may move from here to here. And these electrons, they make up the leakage current. So this is the source of leakage current. And even with this high potential barrier, there may be very high energetic electrons that can move from the source side to the drain side in the off state. So in the off state, ideally the current ID should be 0, but there is practically a current that flows from the source side to the drain side, and this is how we measure it. We apply a very low gate potential, and we apply a very high drain potential. And if you want to measure the leakage current, this is how you can measure the leakage current. So here is a summary of what we have discussed. So this is the curve in the linear region. So in the linear region, if you change VGS from high, from low to high, what will happen is the potential barrier will go down. Okay, so you see here the VDS is constant, and on the other side, so this is the saturation region. In the saturation region, this is the situation. Okay, so where is the saturation region in this graph? It is here. Okay, you see here VDS is greater, so this is the saturation region. It is greater than VDS linear. The VDS linear is down here. It is very small. You see the value here, and the VDS saturated then starts, you see, somewhere here. Okay, so it is above here. So as the drain is at higher potential, it will lower the Fermi levels down in the drain sides, and you have the shape of the potential barrier changes. So this is the shape in the linear region, and this is the shape in the saturated region. So remember that we discussed drain induced voltage barrier. So this slide was the definition of drain induced voltage barrier. So in one of the previous lectures we discussed that what is drain induced voltage barrier, and now we can see what is the actual reason behind the name. So why it's called drain induced barrier lowering. It is called drain induced barrier lowering because, for example, if this is our VDS1 and it is low, and this is our VDS2 which is high, VDS2 is high than VDS1, what will happen? The Fermi level will go down and the shape will change from this to this. So you see the peak is also reduced because the drain side is at a higher potential. It has the effect that some of the electron in the channel, it pulls it towards its side and it lowers the energy of that barrier. Okay, so that's called drain induced barrier lowering, which means that the higher voltage at the drain makes it easier for electron to cross from one side to the other side. So because the barrier is lowered. So this is the explanation. Okay, so let me stop here. This was the part where we explained how a MOSFET operates with the help of energy band diagrams.